Hi everyone, welcome to unit number 9. In unit number 9, we're gonna be exploring correlation and regression and measuring and predicting relationships between two variables. So let's start with this lesson with exploring relationships. So in this case, what we have to do, what we are gonna be looking at is, and let me explain you with this one. We're gonna be analyzing bivariate data. Okay, so we have to see, for example, we have a set of data A, have one variable A, and then we have variable B. Okay, well, in this case, what we're gonna be looking at is at X and Y. So when I change X, how it affects Y. When I increase the numbers, does this increase too? Or when I increase the numbers of X, this one decreases, or there is no evidence that there's any change. So this is what we're going to be doing in this one. This is a correlation. Correlation is measuring how much is really connected A to B. If there's an action, is there a reaction? So we're going to be looking at that, and we're going to be exploring this one by using a scatter plot. Okay, so in the next scatter plot, what we have to do is, for example, here we have x-axis and then we have the y-axis. So in this case, in the x-axis we have a measurement, and then we're going to put all the values. Let's say, for example, here there was 1, 2, 3, 4. Okay, so 1, 2, 3, and 4. Okay, so we're gonna be putting those here. 1, 2, 1, 2, 3, 4, and then of course we're gonna measuring together with this one. There's a 1, 2, 3, and 4. So we're gonna see how that exponential increases. No, so I'm gonna make a perfect correlation here. This is 1, 2, 3, and 4. So I'm gonna measure in that way. If there's a correlation, there's gonna be a straight line out of them. If there's no correlation, then of course, then there's not gonna be a line at all. All right, very good. So in this case, like I said, we're gonna be talking about scatter plots. So in the scatter plots, like I said, we're gonna look at the relationship between them. So we're gonna be looking at this. Let's look at this. Let's look at this data. First of all, we have to understand that we have the right bivariate data. So in this one, we have the number of contacts and the sales. So in this theory, we're trying to prove whether having more contacts increases the sales. Okay. So let's look at this one, if there's any correlation on that one. So let's see, for example, Martha has the largest number of contacts and also has the largest number of sales. So we already can start to see that there's a certain correlation. So in this case, we have, if X increases, does Y increases? So this is X and this is Y. So Bill has 147. We put it here. So, and his sales, so 147 to 126. So we have it here. Then we have Colin and Gary. The same thing. Colin and Gary increase a little bit more, 116, 72. So on this one, we can see already some increasing. Colin here and Gary here. Okay. And then we have Martha. Okay. So in this case, we're gonna throw a line and see how they are connected. So in this case, for example, Colin and Gary start to go. Well, I cannot make this. Well, I think I can make a straight line. Let me remove everything. If I were to do a line here, or if I were to do better, a line here, this is a better line. Okay. Let's do the 3 of them. Let's do the 3. That's the way it should be. We have one line, two lines, and 3 lines. Okay. So if we can find the majority of the data in that means the correlation is strong. In this case, we can see that there's a correlation because they are all going upwards and somehow they are located within that. Maybe clearly not that much, but I mean, and then I'm also not calculating it precisely. But anyways, what we can see is that there's a connection between all of them. Okay, very good. So now in this case, we're going to continue to that. Like I said, we're going to use the scatter plot. The scatter plot has x and y. Here x and here y, x and y. Okay, so very good. So now let's continue talking about this a little bit more. So like I said, in the correlation, we're going to be measuring the strength of the relationship. So in this relationship, what we have to see, like I said, is how strong is that connection. So in this case, we have values. We have different values. Which is -1 and 1. So what we are going to do, for example, is take the bivariate data in Excel. We can use the functions equals correlation. Okay. And then we're going to select all the values in X and all the values in Y. Okay, let's say, for example, here I have 1, 2, 3. Then we put those two columns into the correlation in another cell, and then we're going to get a result. So in this result, we can get, for example, 0.9 or -0.9. So based on that, that means that the correlation is very strong. So it's closing to 1. But if we get any values that is, for example, 0.2 or 0.3 or 0.4, even 0.5 is considered a weak correlation. That means the more you increase X, there's no changes in Y. So in this one, when I do this one, that means that the more I connect, the more I increase X, the more Y will continue increasing. So in this case, we use all this measuring of strength in business to see if there's an action, can we see a reaction. So let's say, for example, we want to measure a correlation if we put an advertisement in a magazine on the left side or on the right side. So we want to know which one has a higher impact. So we do 1 month on the left and 1 month on the right. And then in this case, for example, we're going to see that the sales increase in maybe 7 million. And then in this case, increases in 8 million. So we're going to do this calculation and measure the correlation whether the sales increase or not. This would be only 2 variables. And we're going to calculate them differently. But again, we have to see. Then we can say, for example, in this case, the relationship is stronger. Or let's say, for example, if I do on the left or on the right, I still have 5 million. Regardless, I put it on the left or the right, I make $8 million. So that means the correlation is very low. There's no correlation between putting it on the left or on the right. Okay, very good. So let's continue. Let's continue. So in this case, for example, like I said, we have different types of relationships. So let's explore them a little bit more. So in this case, we have, for example, the linear relationship. So in the linear relationship is the easiest one because simply what we can do is with a line measure how strongly correlated it is. So for example, in this one, we can draw a line in here. And we can see that the correlation here is 0.9. Most of the dots are connecting the line. So there's a strong correlation. We have some values that are a little bit outside, like Florida and New York, but somehow that's nothing to worry much. But if we look at the other one here, we can see the oil, gas, and correlation in this linear correlation is very low. It's already 5.8 or 6, which is not that strong. So if we draw the same line again, in this case, we can see that the values start to be more far away from the line, meaning the correlation is weaker. Okay, so in this case, this is the easiest way to spot it with a linear relationship. Now, let's look at the next one. In the next one, we're gonna look at no relationship. In a no relationship is also very easy to measure. In this one, we have a correlation of a In this case, we have a correlation that is 0.2, which is very low. That means there's no connection between two things, between last week market return and this week market return. Why? There's no correlation because they are independent events. So we have to measure that. We have to understand that also from previous units, whether they are mutually exclusive and they are non-dependent events. So in this case, if we draw a line, we can see that actually many values go into different directions. So in this case, we can measure that, yes, there are a couple dots in here that somehow make it happen, which stands for that 0.2, but in general, many of the points are not even going into that direction. So that's when we can approach this as a no relationship when we have a very, very low value. Now, we have nonlinear relationships. In a nonlinear relationship, we can say initially that there's no connection between them because it's 0.1. So actually it's very low. But when we look at it, actually it is not. What we have to look at it is that here there's a nonlinear one. There's a relationship, but it is more going into one direction and then another direction. Let's put it this way. Okay, so if you can see, then the evidence is clear. We cannot say there's no correlation. It means all the way up to this point it correlates positively, and all the way to here correlates negatively. So what we have to do is perhaps divide the data and see why at this point of data it starts to change. We have to analyze why. So in this case, it's better to separate the data and try to overall see what is the trend or why, or what is the breaking point. In this case, for example, I can say, let's look at the marketing case. So the more I advertise, the more sales I generate. So if I advertise 30 million, that's good. People start to buy more. But more than 30 million in advertising leads in customers already fed up with watching my videos, my advertisings everywhere. Like, for example, here in Korea, we can see with the K-pop artists, you start to get fed up that they appear selling glasses, insurance, banking, any kind of thing. So in this case, it starts to decline. So more than 30 million in advertising means that there's a sharp decline because consumers start to lose interest into that. So that is how we can interpret this. Now, let's look into unequal variability. Unequal variability happens with very large data sets. Why? Because it happens that at some point of it, the data is very narrow, it's very tight. If we can see here we can see all the data is very tight, but starts to spread. So whenever we have this, that doesn't mean that there's no correlation, but what we can do is we have to somehow normally distribute the data. So this one you already have learned it before. So what we're gonna do is transforming the data. Perhaps we're gonna use the logarithm scale. We're gonna change both the x and y. We're gonna change them to logarithm, and then we can see a more beautiful connection between the data in here. So in this case, we can see it this way, no? So we can see that already the data starts to be much more correlated. You see the difference here already. You can see the difference because when we're looking at this, for example, we can see here the correlation is 0.7, which is not bad, but because of this variation, it's not completely accurate. But in this case, once we have the accurate data already set up, we can see that it's 0.8, right? Okay, that's good. So now let's continue. Here we have, for example, clustering. In clustering, what we happen is that we have two sets of data. So remember, in this case, the last time we talked about bimodal distribution. So this is the equivalent of bimodal distribution, but in correlation. So as we can see, we have two groups. Okay, one group, two groups. So good correlations, but they don't match. So in this case, what we have to do is treat them separately. Perhaps we can have to divide the data, treat them differently, and then, of course, that will lead a much accurate result. So we have to think of that whenever we have this one. The same thing. It seems as bimodal distributions, we have to make sure that they are separate significantly and that they have sufficient data. Otherwise, if there's no sufficient data, it means that they are just probably outliers, and then we have to fix it. Whenever we are working with correlations, we have to make sure that also the data is normally distributed or close to it. Otherwise, we cannot do it. Okay, very good. So now let's continue. Let me clear all that. This shouldn't be there. So this one we have there, the clustering, and then let's go to bivariate outliers. So in this case, we also have outliers. But we don't call them just outliers. We call them bivariate outliers because on both on X and Y, they are too high values or too low values, and they are causing some trouble. So in this case, you can see, for example, correlation is minus 0.6, so it's still very low. If we try to assess it, yes, we can see there's connections in here, but these guys are changing. That guy is changing this number. Now, when we fix it, when we remove it, we have 0.8, and then we can see a very different approach, as we can see a line that perfectly correlates the value. So in this case, what we have to do is to remove it, or if we cannot remove it, then we have to logarithm the data, so at least it becomes approximately normally distributed. So now let's go to the next one. Then we have correlation and causation. Then we have to understand that correlation, that two things are connected, that doesn't mean it's the cause of it. So here let's look at, for example, at this case. In this case, it's very, very funny. He says, the more fresh lemons we import to USA from Mexico, the number of accidents is gonna decrease. Yes, the two data are perfectly correlated, but that doesn't mean that's the cause of it. So in business, we always have to be very cautious about it. That although the data seems to have a good correlation, that doesn't mean that's the cause of it. So in this one, we have to be very critical and go a little bit more analytical, and rather than just quantitative, also we have to think qualitatively, why is the reason of that. So in this case, there's no reason for that. Fantastically correlated at 0.97, almost 1, but the reality is that this has nothing to do with this. You took data that doesn't match, and that happens in the real life. We match data, or we have two variables that are never even connected, and then we can say that. No, so in this we can say, for example, the number of employees that wear a red cap makes it more productive, make more productive the company. So in this case, what you're not analyzing is that the people that has a red cap perhaps has more years of experience. So that's why they wear a red cap, but not because of they wear the red cap. So what happens if, for example, you go and take an approach of giving red caps to all of your employees, and then you don't see any increase in productivity? It's like, oh, but we thought because of the red cap. Yeah, there's a perfect correlation, but it was because actually you were measuring the years of experience. So if we measure years of experience, the more years of experience that we have, the more productive they are gonna be. That's a good correlation, but not because of the red cap. So in this one, you have to be very critical about it, and you need to understand this concept very, very, very well. Comes in your exam. So let's go to the next one. So correlation doesn't mean causation. So let's look at the slope of regression. So we have to, in this case, we're gonna understand how to interpret the slope of regression. In the slope of regression, what we can see is that, for example, the slope is 2. So in this case, we can write it as 2 as 1. So in this case, as the value x increases by 1, then the value y increases by 2. Okay? So every time, let's say, for example, I spend 1 million in marketing, I'm going to see 2 million in sales. Okay, so that's how we interpret the slope of a regression line. So in this case, like I said, that is how we interpret that line that we were looking at, that slope of a regression line. So that was this, that the regression is somehow the connection. So now let's talk about the standard error of estimate. The standard error of estimate works very, very similar to what we do in the standard deviation, but in this case we have a v-variate data. So the only thing that we're going to be looking differently into the standard error of estimation, we're going to look at variability as well. So how far are the values in average compared to the original line? So this is what I was explaining to you earlier today. So we have this line, and the standard error of estimate estimates how far is from that line. So here, for example, if there's a couple of values in here, then if there's a value in here, if there's a value here, if there's a value here, then of course the standard of error estimate will increase. Why? Because in this case, if we have, again, let's do more lines. Let's do one line, one more line, one more line, one more line. Then in this case, the standard error of estimate will be much larger. Okay, so in this case, we can see, for example, in this line, the standard error of estimate, many of the values are somehow near, so somehow the standard error of estimate is going to be very low. So variability is going to be very low. So now let's continue with R squared. So in R squared, pretty much we use it, the regression, we interpret it as R squared. We're going to look at that later when we do somehow our Excel. But anyways, in R squared is, we try to figure out if, like I said, the connection between X and Y is strong, and that it didn't happen by chance, by accident. So the stronger it is, pretty much we can say that the relationship is stronger. Now, in this case, however, in practice, a small r squared does not necessarily say that X is not helpful in explaining Y. It is just that merely signal that Y is also partly determined by other factors. So somehow, sometimes, this is where we have to do a multiple regression analysis. Correlation, in this case, for example, let's do it with a square. We have data X, data Y. So we can say that, let me make it small. This is data X. Okay. And this is data. It's not doing it. Y. Okay. We have two variables there, X and Y. And we see in R squared, we see a very little value, someone that is very, very small value. So in this case, that doesn't mean that there's no correlation, or the correlation is little. That doesn't mean that there is no connection. What this means is that perhaps there might be other perhaps that there might be other variables that affect that. Okay, so in this case we can see that, for example, C and A and B also influence the sales of Y. So in this case, for example, we can say, so putting more advertising or spending more on marketing increase our sales. But once you calculate it, you realize that the correlation is very slow. So when you start to add more things, like for example, the people that view the advertising, the places that the advertising was well, the number of times that the advertising was shown, etc., etc., then we have to add more things. So in this case, this is when X, C, A, and B change Y. So in this case, we call it a multiple regression analysis. Okay, we're not gonna see multiple regression analysis this semester that much because well, not that much. We're not gonna see it at all because in the end, this is way more complex and it requires a lot more statistical information that we don't have the time to do it. So in this case, like I said, whenever X and Y is low, we have to explore if there's any more things that actually are changing this. So in this case, what we have to do is see whether X, Y, and B all together, and then we're gonna have a very different calculation. But in this case, like I said, we just have to be critical whether it is not connected for that specific reason or whether there are more reasons that we have to include. Okay, very good. So with that one we're done for the day. And yep, so you can also look at well, this is the short video lecture. You can look at the different things, and well, that should be all for today. If you have any questions on this, please let me know.